Thank you, Yun. So my talk is going to go down some of the same roads that we've gone down, and maybe from a little bit different direction. I think we saw a sort of overarching view of the industry from Gary. Dave gave us a really good insight into some of the traffic demand and where it comes from and where it's likely to go. And now I want to take a step down, not really talk about technology, but talk about sort of how technology gets used and why we might need to use various technologies. This slide here is a picture of Crawford Hill, where I've had the good fortune to spend a lot of my career. And the building was designed by a man named Rudi Kampfner. He was an Austrian, was at Bell Labs. And in 1965, he wrote a paper about optical communications. This is when lasers are brand new. There's no optical fiber. And he actually sort of foresaw wavelength multiplexing, coherent detection, and many of the things that we now only just recently have brought to fruition. So at an early day, a technical visionary could sort of see that, wow, the carrier frequency of a laser is really high. There's a lot of bandwidth there. And so I'm not really going to be talking about, from a science perspective, how these technologies became available, but how it looked to the people when they were trying to decide what to deploy next. So let me get going. First, I want to acknowledge some various people that have helped me with this over the years to think about these topics, and they're listed on the left-hand side there. And most of those are folks from Bell Labs. I want to add a couple people. Larry Coldren, I was able to get a little time with yesterday, and he had some nice things to say, and Roger Stolen as well. And then on the right-hand side are some references that were very helpful in compiling what I've got here. The Bell System Technical Journal, I've got some screenshots, and I think they're going to be entertaining. And the Alcatel-Lucent archives, there are great photographs in there going all the way back to the early days of AT&T. And then finally, I want to mention City of Light is a great book if you're interested in historical development of our field. Jeff Heck did a great job in that book. Okay, so what am I going to talk about? I'm going to talk about where we are in the optical communications industry and what is the likely evolution. I'm going to make the point that where we are in terms of the development of the capacity of single-mode fiber systems is we're getting to where there isn't a heck of a lot of capacity to be wrung out of a single-mode fiber anymore. I'm going to try to convince you that that's basically true. And then what's next is the question. How do we make a decision for what technologies we can deploy next to try to continue the increase of capacity? And I want to address that by looking back. In 1975, optical fiber came in and revolutionized long-distance communication in a very short period of time. It took over. And I want to take a look at what happened, what it looked like just before then. We were looking at different options that we had for technologies. How did we kind of make the decision which way to go? And then I'll look at 1989, where optical amplifiers and WDM, again, revolutionized the industry. And what did it look like just before it was obvious to everybody that that was what was going to happen? And then we'll try to see if there are any lessons to draw from today, although most of the lessons are going to be left as an exercise to the listeners. So bandwidth seems to be an insatiable demand, and Dave has covered this topic really well, so I don't need to talk about it too much. But that's been independent of what all these applications have been. This slide is a little bit old, the way I've structured it, starting with email and web browsing, and then music and video sharing, and of course now streaming video. But if we look at the traffic growth over the years, we don't really see those applications coming in as significant drivers. What we see is something that's kind of flat, except for that really anomalous point back in the mid-90s when the public internet just kind of got going. And that growth rate, I label it on here as 2 dB per year because most of us are engineers here, so dB is a nice way to think about things. And what that means is that in 5 years, you see a factor of 10 growth. And that's kind of roughly consistent. Dave mentioned the Cisco Visual Networking Index, which is the yellow triangles there, and you can see that it is drooping over their predictions into the future, go down to maybe even only 1 dB per year. But in any case, we're talking about, you take 10 years, you're starting to talk about a lot of growth. And I want to think about, what are we doing for 10 years in the future as we go here. So why does it keep growing? And Dave's talked about this as well, so I don't really want to belabor the point. But much of the traffic is between machines, and I don't necessarily mean your furnace, but instead a computer that has a lot of data on it in one place and another database that's in another place that needs to synchronize, or they're moving movies to the caches so people will be able to get them. And those machines get faster every year, and of course we all know that. The traffic growth, the processor speed is going up at about 2.5 dB per year, as shown exemplified here by the top 500, the fastest supercomputers around. Or another way to think of it is just when there's more data to communicate. And the bottom chart is from an IDC report called The Diverse and Exploding Digital Universe. They tried to capture how much data there is out there, and they find that that grows at about 2 dB per year. So I think the fact that all those numbers are around the same is not a coincidence. It's because, as Dave said, when the capacity is there, the applications come in and use it. And the capacity is being driven by these fundamental technologies of Moore's law and so on. So now let's talk about the capacity of optical communication systems. This chart shows the capacity that can be transmitted on a single fiber in research demonstrations from this conference and other major conferences. And these, I've tried to pick only the records, so we don't have a lot of points. We just have the ones that are the best at each particular time. And you see that the blue dots were single channel systems in the early days of optical communications, excuse me. And then the red ones are WDM systems. And when WDM started, of course, it was very easy to make progress. You started with one channel, you go to 2, 4, 8. You can really go like gangbusters until you get about as many channels as you can fit in, say, an optical amplifier bandwidth. And then it gets harder. You have to be more efficient about using it, and that's why you see that level off like that. The next chart shows what happens when we look at commercial deployments, what products were available when. And the great part about this, the thing that I think is one of the really good takeaway messages from this talk, is that this industry, the research in this industry has driven commercial practice in a very predictable way. About 5 years later, after a research hero result is demonstrated, we start to see a product like that. And that's something that I think all the people who've been in this field for years can take a lot of pride in. So now I want to talk a little bit about the traffic again. And I want to just consider both voice and data traffic just to get a total traffic. And I simplify it, take all the wiggles out of it, and just extrapolate curves. So I have that 2 dB per year for the data calibrated to 2002, and I have voice underneath at 8% a year calibrated to 2002 when I had pretty good numbers. And you see a nice curve like that. Now what I want to do now is superimpose on that traffic curve, the blue one. The red lines go through the data points for the commercial systems. And this chart has a lot to recommend it to think about. The most remarkable thing is that in the year 2000, a single fiber optical communication system could carry as much traffic as there was in the North American network. And that shot right through there up to where it was maybe a factor of 5 times more than the traffic in the network. And then in 2008, the traffic started growing as the data really overwhelmed the voice, and the traffic in the network, again, got bigger than what we could carry in a system. So now if you look at that and think about, so this tells you what happened to our industry in 2000. All of a sudden, everybody had to get one of these really great high-capacity systems, but once they had one, they didn't need another one for quite a while. And we saw, if you now take I once constructed a model where you just look at how many systems would you sell to cover a particular network if you took the highest capacity one you could buy every year. You see that the market drops to nothing in around 2000 and doesn't come back till around 2005 or so. And that's really what happened. It's a very simple numerical thing that caused that. It wasn't really a tulip mania or anything like that. So I've said that the rate of capacity growth has really fallen down, and it's because you have to be more efficient in how you use capacity. And this is that efficiency. It's how many channels you can put in, the bit rate of those channels divided by their channel spacing. And we see that that's been increasing in research demonstrations at about 1 dB per year. And that's less than the traffic rate. Now you could say, well, Cisco's saying it's going to be only 1 dB per year. Maybe it's okay. Maybe the spectral efficiency of the systems can continue to increase at 1 dB per year. But it's not likely to continue. Right now, the best commercial systems are operating at about 4 bits per hertz spectral efficiency, and there just isn't that much room, and I'll try to substantiate that a little bit more. So if I want to increase the spectral efficiency of a system, I'm going to look here at some bit rates that you can achieve at 28 GBAUD. So for a QPSK, that's the 100G coherent systems that we're deploying aggressively now. And just recently, 16 QAM systems, the second from the right, are giving us 200 gigabits per second on 50 gigahertz or 37 gigahertz spacing, getting us up to 4 to 6 bits per second per hertz. But if we want to keep increasing that, you can see there's more and more dots. They get closer and closer together, and it just gets hard. And this chart shows how the reach of a system, for instance, will change as I go up that ladder. I go to more and more complex constellations. I start with 100% reach, and that for a binary system, binary phase shift keyed system that just has 2 dots, I get this reach. If I go to polarization multiplexing, I don't lose anything. I have to put twice the power in for the other polarization, but the energy per bit stays the same and my reach stays the same. QPSK is essentially the same thing. It's another orthogonal dimension. I'm using quadrature. But as soon as I go to 16 QAM, I lose about a factor. Go down to about 40% of the reach that I could achieve for those simple constellations. If I go to 64 QAM, I lose another factor of 3. And you see that trying to go out that ladder is really a fool's errand. I'm exponentially losing, and I'm not going to be able to go very far out there. Where I end up operating depends on how good my coding is and so on. But you can't count on getting a factor of 10 by going out on that axis. So that's essentially the Shannon limit. This capacity of a system is proportional to the log to the base 2 of 1 plus the signal-to-noise ratio. So you might say, well, as long as I can improve signal-to-noise ratio, that's great. But optical communication systems involve amplifiers. I have a transmitter and receiver with a certain amount of loss between them. I have amplifier gains that I can tolerate. So each of those amplifiers puts noise on, and I have a certain amount of noise at the end. And then to get a better signal-to-noise ratio, I have to put in more power. And as I put that more power in, I start to see nonlinear occurrence in the fiber, which creates additional noise effectively, and that ends up limiting the capacity. So as I increase the signal-to-noise ratio, or the power in the line, eventually the capacity rolls over. And the next chart shows you a fairly precise calculation of the capacity of that system. This is done by René Siambre for a polarization multiplex system, 500 kilometers long. And you see that there's a maximum capacity there of about 17 bits per second per hertz. So that's first statement, is there's roughly a maximum capacity. The dots in there are the best experimental results, these hero results that I've talked about. There's one at about 11 bits per second per hertz. So we're less than a factor of 2 away from the limit of what you can expect to achieve. Now those are over somewhat shorter distances and so on, so there's more improvements, but there's no factor of 10 there. No factor of 10 for more capacity that way. And the best commercial systems are only about a factor of 2 behind those experiments right now. So we're very close to what we can wring out of single mode fibers. So let's think about, is there some way that we could use fibers to improve this? Can we get better fibers that'll have higher capacities? So in this chart, I compare 2 fibers versus 1 fiber with twice the area, because twice the area would allow me to have a lower power density, less nonlinearity. Well, 2 fibers obviously have twice as much capacity as 1. And a fiber with twice the area can support twice as much power. So twice the power gives me 3 dB better signal-to-noise ratio. And if I plug that into the Shannon limit, you can see that the signal-to-noise ratio, if it's already large, making it twice as big just gives me 1 more bit per second per hertz. So if I'm operating at 11 bits per second per hertz, I go to a fiber with twice the area, I go to 12 bits per second per hertz, and virtually no increase. So this chart just shows trying various things, making the loss of fibers lower, the core area larger, or the nonlinear index smaller, which is the same thing, or increasing the dispersion, because chromatic dispersion really suppresses nonlinearities. And you see that all of those things, we're looking at logarithmic axes on the horizontal axis and linear bits per second per hertz on the vertical axis. You can see that you really can't make any significant strides this way. Better fibers is not going to allow you to get a factor of 10 more capacity. So what can we do? In communication systems to date, we've explored using quadrature to get more capacity. We've shown how that's difficult to continue with. We use wavelength multiplexing. We use polarization multiplexing already. We could try to use more bandwidth. Right now, we use really mostly only C-band systems. We can go to C+L systems. And an important way that you can experimentally check whether anything I'm saying makes any sense is whether people start deploying some C+L systems in years. People that don't have a lot of fiber will start, I think, looking very hard at wanting to do C+L systems. And then after that, we have to do something in the way of spatial multiplexing. That's really all that's left. Using parallel fibers and putting in parallel systems is a form of spatial multiplexing, although you're not going to save very much that way. Multi-core fibers, as shown there. If the cores don't interact, I can get n times the capacity. The next possibility is to use few-moded fibers or maybe multi-mode fibers. And in fact, you'll see a post-deadline paper here where people use an actual conventional multi-mode fiber and do spatial multiplexing of 12 modes. But I just want to make the point that spatial multiplexing is out there as a possibility, and then I want to think a little bit about whether that could be the future. Well, if we look at the research capacity demonstrations, those blue stars are now on that previous chart. Those are SDM results, so that looks good. Looks like research results are starting to come along. It offers the possibility to increase the capacity, but does it reduce the cost is the question. Does it give us any real benefit? Because just setting new records for fiber capacity isn't necessarily in anyone's interest. Well, the value proposition for spatial multiplexing really depends on integration of some kind. Okay, integrating the fiber is one thing, but that's really a kind of a small piece. Amplifiers, for instance, are critical. The reason that WDM was such a great thing is that you could eliminate however many channels you had, 8 channels, say, 8 regenerators for one amplifier. And we have to have that same kind of economics for SDM. So we have to have amplifiers that amplify spatial modes and wavelengths just with one device. Wavelength selective switches, transmitters and receivers, all of these people have demonstrated technology. And if you go to various sessions here at the conference, you'll see SDM results in all of these things. And that integration is what would make SDM a cost-effective alternative. So is that the future? I want to now think about, by looking at these historical examples, can we illuminate this? So let's look back to 1975. In 1975, coax and microwave systems are extensively deployed, and they're providing good capacity. We're looking at millimeter waveguide systems as a possible next generation. And then fiber optics research is starting to be promising, but it's not really quite on people's radar screens as an alternative at that point. This is what coaxial cable systems looked like in 1974. First of all, they're analog, and digitization actually is one of the major things that drove fiber optics, because when it was introduced as a digital technology and provided a reason to actually move off of microwave and coax. But in any case, coax systems in '74, you could do about the equivalent of 6.8 gigabits per second in a cable like that one. So that's actually a fairly high capacity system. The table on the bottom is one of these screenshots from the BSTJ, and it tells you what some of the characteristics of systems introduced from 41 up to 74. And you see that capacity went up very nicely over there, but the repeater spacing went down very dramatically, 8 miles, 4 miles, 2 miles, 1 mile for this L5 system. So it was starting to become operationally more difficult to cram more and more capacity into those cables. Microwave systems were also ubiquitous at this time, giving about 2 gigabits per second of capacity. And so that's, again, a fairly large capacity. These were also analog systems, and I'm sure many of you remember the Sprint ads of blowing up microwave towers because they were going to an all-fiber network that was all digital, and that was one of the things that really drove fiber. So what were the successor systems at that time? Again, people who were living with coax and microwave, the successor system they thought about was this millimeter waveguide system that could carry very high capacities. Bill Warders wrote an article about it, and I'm going to come back to this article, so I just wanted to flash the title. And this is a description of these systems. They were designed for 17 gigabits per second of capacity, so it's a fairly large capacity at that time. A 6-centimeter diameter waveguide, and it had to be pretty straight. So you see, as it's laid out in a test here, many, many mounts to make sure that the thing is perfectly straight, and the curves could be very well controlled, because if the waveguides had too much of a bend, there'd be a lot of mode conversion and impairment of the system. So it took a lot of care to minimize the loss, but it had a repeater spacing of 50 to 60 kilometers. So it's actually quite an improvement over the coax systems at 1 mile. Now we're out to 50, 60 kilometers. And you could double the capacity of this system, and that was a trial that was done in 71 and 77 as well, of going to 34 gigabits per second by using QPSK. So it's a very high capacity system. But here's the rest of that, the next piece of the article from Warders, where he talks about technology of this system has been pretty well solved, but the economic ones have proven much more formidable. And in recent years, growth has been very rapid, but the recession is on in 1977, and they're seeing not so much a need for capacity. And so it isn't really clear when this waveguide system would be deployed. So the reason that this system is not going to be deployed is because they don't really need 34 gigabits of capacity. Here's a picture of a field trial of fiber optics at roughly the same time, 1977 in Chicago. A 45 megabit per second system was being deployed over a fairly short distance. It's multi-mode fiber. But one of the really interesting things about this is that the fiber is being pulled off a spool and pushed through ducts in Chicago. The ducts aren't even dry, they're wet, and they're just throwing the fiber in there. This is a lot easier than that millimeter waveguide system. That's one key thing. It's going to be much cheaper, obviously, to deploy. And they could get 6.5 kilometer potential regenerator spacing, not quite as good as the millimeter waveguide system, but still much better than the coax. So this is now those research capacities with the capacities of these various options that were available in 75. You see the fiber down there at 45 megabits per second, or maybe they used 12 fiber ribbons, so I can multiply that by 12 and move it up one division. Then there's the microwave systems at about 2 gigabits, coax at 6.8, and the millimeter waveguide, 17 to 34 gigabits per second. So you see that the capacities of those electrical communication alternatives are actually much higher. But you also can see that those weren't going to reach, we didn't end up reaching those in optical communications until much later in the 80s and 90s. But at the same time, the capacity of the fiber system was actually enough for what was needed. So let's fast forward to 1989. In 1989, there are single channel systems at 2.5, or at AT&T at the time, 1.7 gigabits per second, because it's before SDH really started to be used. And they're extensively deployed. Occasionally, they use two wavelengths, 1.3 and 1.5 microns. Higher speed systems are being actively developed as the next obvious step to go from 2.5 to 10 gigabits per second. There's a lot of effort on the high-speed circuits, and we're worried about chromatic dispersion and polarization mode dispersion, limiting the repeater spacing. WDM is also kind of on the table as a possible path, and the reason that it comes in is because it offers a lower growth path. Instead of having to go all the way to 10 gigabits, you could go from 2.5 to 5 or 7.5 as you needed it. That was a very attractive thing at the time. Optical amplifier technology, of course, comes in and just changes the economics totally, and WDM takes off. And from there, things grow very dramatically. Here's a slide from Ting-Yi Lee. He has gone through the history of this particular revolution in many talks. I hope you had a chance to see them before he left us. And there was a thing called Project Ultra at AT&T at the time to develop an 8 gigabit per second system targeted for deployment in 92. 1.3 micron DFBs, gallium arsenide APDs, gallium arsenide or silicon bipolar ICs. But in 88, the project was terminated because, gee, we just really don't see when we're going to need an 8 gigabit per second system. So they immediately started a new project to get all the research people back employed and feeling optimistic again on WDM. And this is a slide about the field trials, and I realized I needed a nice picture, so I put in a picture of the Roaring Creek Earth Station where the field trial actually happened, and the satellite dishes have nothing to do with it, really. But there were two trials done at this location, one in 1989 and one in 1991. In 89, the trial was not terribly impressive. There were 4 channels, but they were using a frequency shift keying scheme with an optical filter because there weren't good modulators available, and the amplifiers were at the very beginning. They weren't that great. But by 1991, there were very good amplifiers, and there were some good external modulators, and an 840-kilometer system could be put together. And that really convinced everyone at AT&T, anyway, that it was time to go down this path for WDM. And in 92, here's a shot from a technical memorandum, another thing I pulled out of the archives, where someone's doing a systems requirement document. So this is, the guys who are actually going to deploy the thing. And you can see that essentially going down this WDM path is the plan of record for them. So very quickly, things flopped from the plan of record being this high-speed system to being this WDM system. This next slide is the title page from a technical memorandum by Alan Ganauk. And what I wanted to illustrate with it is that people were thinking at this time that it was sort of high speed versus WDM, like they were two competing technologies, and we had to decide which one to deploy. Alan's first sentence there is, despite the current attention devoted to wavelength multiplexed optical communications, it is still important to work on these high-speed systems. So he felt he had to sort of defend his high-speed work because everybody was thinking so much about WDM. The next slide is, again, these same research points. And since I kind of impugned Alan Ganauk by making him look like he was defending old technology, I want to just make the point that all those ones circled in yellow are records that Alan Ganauk was involved in. So obviously we owe a lot to him over the years. But the point I really want to make here is that once the WDM system started being explored in research, very quickly those points going up steeply are 10 gigabits per second, 20, and 40 gigabits per second per channel. So high speed and WDM turned out to be the answer. It wasn't really either or. But back in 1989, 1991, it was very much either or, and the decision was made to go with WDM because it was perhaps a lower capacity solution. So this is a theme that I wanted to extract from both those things, that when these decisions were made to go with fiber versus millimeter waveguides or WDM versus high-speed systems, it was partly because the demand for capacity wasn't there, so they were looking for something that was a smaller bite of capacity to take and a simpler kind of an upgrade path. in both cases, the capacity growth really came in and was needed, and optical technology met the challenge. So we made the right decisions in those two cases, but we made them for the wrong reasons. We didn't really know why we were, well, we knew why we made the decision, but we didn't actually do it for the reason that ended up being very important. So, the next generation of optical communications. Is SDM the next WDM, or is it the next millimeter waveguide? That's kind of the question I'm teeing up here for you guys to all think about. So millimeter waveguide was the obvious continuation of the electrical systems of the day. It was the next step using a more fancy media, had very high capacity, but it was kind of expensive and difficult to deploy. So we think about SDM. It continues optical communication heritage. We're using many of those same techniques, so it has that sort of in common. Does it require new fiber? Well, not necessarily. I described how many of the cost savings in SDM may come from the amplifiers or other things, and maybe we could even use parallel fibers if we want. So maybe it doesn't require new fiber. But, and also, another point to make is that when WDM came in, it didn't require new fiber really per force, but we ended up deploying new fiber throughout the country and throughout the world for WDM, these non-zero dispersion shifted fibers. Fiber was replaced in that generation, and that fiber might be replaced in our next generation should not really be something that we think is impossible, I think. SDM is kind of complex. The MIMO processing that's involved in the multi-mode fiber systems involves a high level of digital signal processing. High level of optical integration is going to be required to save money. But those things are going to be really important no matter what. We're going to need integration and cost reduction, because the only way to keep getting the cost per bit going down is to do some very dramatic things. So DSP perhaps is an enabling technology for this in the way that amplifiers was for WDM. If DSP continues, and I think none of us really want to bet against what the capabilities of DSP will be in the next several years, it may be what makes it possible to use SDM. The other thing we have to look at is, I teed these other ones up that there were two options and people had to make a decision between them. Right now, we don't have another option than SDM. So there probably ought to be more options out there that we could think about. What would be another way to get more capacity? But it isn't clear what it is, and I think we should be on the lookout for that. At one point I was involved in a patent, and the patent attorney came back. We had set it up that it should cover optical fiber systems like this, or silica fiber systems. I think we said glass fiber systems. And he came back and said, you know, I don't want to have glass in there because, you know, maybe carbon fibers with X-rays are going to be the right way to go in the future, and he wanted to make sure that the patent would still be good. So we thought that was ridiculous at the time, but at the same time, what is there out there that might be completely different, and maybe that's happening in some other conference now that is going to come and supplant us? I'm not sure what it is, but we should keep an eye out for it. In any case, that's really what I wanted to do, give you guys a chance to think about what you think about these technologies, and try to, as you go through the conference, try to find the things that will be the most interesting, and see where we go from here. Thank you.